AMD has officially announced the production ramp of its next-generation EPYC processor codenamed Venice, built on TSMC's advanced CMM process technology. This is not merely a marketing update for server rooms. The real stakes involve whether this silicon can finally solve the physical constraints preventing mobile robots from achieving true autonomy. By the end of this analysis, you will understand exactly how the transition to SecM shifts the failure modes of edge computing and why the current power-to-performance ratio is the critical variable for unventilated mobile chassis. For years, the robotics community has been stuck in a cycle of theoretical capability versus physical reality. We can design algorithms that perceive the world with incredible depth, but the hardware to run them locally remains a bottleneck. Mobile robots operate in unventilated environments where thermal runaway is a constant threat. If a processor generates too much heat, the system must throttle performance, leading to missed frames and delayed reactions. This latency is fatal for autonomy. The industry has relied on external PCIe bridges to offload heavy lifting, but those connections introduce inter-chip latency and power loss that simply do not exist in a tightly packed mobile robot chassis. Here is the thing about the Venice announcement that most spec sheets miss. This is the first high-performance computing product to utilize TSMC's N2 node. That specific manufacturing milestone is not just about transistor density, it is about a fundamental shift in how I/O is handled. The architecture reportedly delivers a 2.5x increase in I/O density compared to the previous 5nm generation. To put that in perspective, this means the bandwidth available for sensor fusion, like LiDAR and high-resolution camera feeds, has effectively tripled without the traditional power penalty that has plagued previous nodes. Consider the power per instruction curve. The Zen 6 architecture, when paired with the SecM process, is projected to sustain 90% of peak compute performance while operating at only 30% of the thermal design power of current 5nm EPYC chips. This is a massive shift. For a mobile robot, this means the system can sustain high-frequency perception tasks without triggering thermal shutdowns. The constraint is no longer raw compute availability. The constraint is now dynamic voltage scaling algorithms capable of handling localized hotspots on the CMM substrate during bursty perception tasks. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The chiplet design of Venice is another crucial detail that distinguishes this from competing silicon. Reports suggest the die size is smaller than comparable Apple silicon solutions, which translates to superior efficiency per watt. This efficiency allows system architects to consolidate the edge inference engine and the high-speed I/O controller onto a single die. Eliminating the need for multiple chips to talk to each other removes the inter-chip latency that has been a persistent issue in current multi-die mobile robot systems. This consolidation is not just a convenience, it is a necessity for sub-millisecond latency requirements. However, we must separate the manufacturing milestone from real-world deployment data. The silicon has been taped out and validation is underway in Arizona, but we are still in a window of theoretical efficiency. There are no benchmark results quantifying latency improvements for specific robotics workloads yet. The available evidence confirms the process technology scaling, but it does not yet provide empirical proof of robotic performance. The timeline for full platform availability targets a launch next year, leaving a gap where the theoretical benefits cannot yet be validated against the rigorous demands of mobile robotics. This leads to a significant knowledge gap regarding the timeline for adoption. While the silicon is ready and the architecture is confirmed, the ecosystem must catch up. The transition from 5nm to SecM changes the physics of the system. As power density increases, the primary failure mode shifts from overheating to voltage instability. Engineers will need to develop new algorithms to manage localized hotspots on the CMM substrate. This is a new problem space that requires a different approach to system design than what was used for previous generations. The co-optimization strategy employed here is also worth noting. The memory controller and fabric are physically tuned for the specific latency constraints of real-time SLAM algorithms. This is not just about raw throughput. It is about ensuring that the data pipeline for simultaneous localization and mapping does not stall under load. By aligning the physical layer with the algorithmic requirements, AMD is attempting to solve the latency bottlenecks inherent in edge computing. This approach suggests a future where the hardware is designed around the specific workload of the robot, rather than forcing the robot to adapt to the hardware. The implication for investors and engineers is clear. If the Venice platform delivers on these projected metrics, it represents a fundamental enabler for next-generation robotics. It allows for complex models to run on-device without cloud dependency, removing the latency of network round trips. This is the difference between a robot that reacts to a moving obstacle and one that anticipates it. The ability to process sensor data locally with high speed and low power is the key to unlocking true autonomy in unstructured environments. Yet, the skepticism remains warranted. The claim that Venice solves current autonomy constraints is currently a projection based on process technology scaling rather than empirical evidence of robotic performance. Until we see real-world deployment data, the transition to SegM remains a promise rather than a proven solution. The industry must wait for the launch next year to see if the theoretical efficiency translates to practical success. The shift in failure modes from raw compute to dynamic voltage scaling is a signal that the next generation of robotics will require a new level of software sophistication to match the hardware capabilities. The production ramp of Venice marks a pivotal moment in the evolution of edge computing. It validates a strategy where the chip's physical design is optimized for the specific latency constraints of real-time applications. This is a move away from generic high-performance computing towards specialized edge intelligence. The success of this platform will depend on whether the ecosystem can adapt to the new thermal and voltage characteristics of the SegM substrate. The potential is there, but the validation is still pending. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.